The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI Conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI Conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Okay, our next speaker is Doug Hooton. He's from, Doug doesn't need any specific introduction, but he's from University of Toronto. He has plenty of experience on the ASR durability aspect, and he's going to talk about the Kingston outdoor exposure site for mitigating ASR after 20 years. Welcome, Doug.
Good afternoon. So I'm going to just talk about, we started the project about 20 years ago. It was Chris Rogers who was the petrographer at the Ministry of Transport in Ontario. He's now retired, and so Caroline McDonald has taken over monitoring that site. I was involved with Chris in helping design some of the layout of the project. Terry Ramlokin, who did some of the petrographic work on the analysis of some of the cores we took from that project. I'm only going to talk about the ASR part. We actually looked at things like chloride diffusion and freeze-thaw resistance, de-icer scaling, because the ministry was looking for solutions for ASR, but they also were concerned that if they used high-volume slag replacements, which is the most common SCM in Ontario, that they would perhaps run into other issues, and they wanted to know what that was, and it actually improved chloride resistance, and the scaling resistance wasn't much. There's Chris there, standing on his site. We used 6 different concrete mixtures. It was placed at a Department of Transport site in Kingston, Ontario. And we did sidewalk slabs, 4 of them showing there, and we did a series of large blocks. They're about 600 millimeters by 600 millimeters by about 6 feet long. There's the mixed units for you. And we did reinforced and unreinforced beams. The reinforced beams had about 1.4% steel area longitudinally, and we had DMEC gauges buried in both the sidewalk slabs and in the beams. There were 6 mixes, as I mentioned. I got them in the order we placed them. We had a high-alkali Portland cement, which we then used with 50% blast furnace slag. We used one that had 18% fly ash. We didn't pick 18 because it was a good number to use. We picked it because that's how much fly ash we had available at the ready mix plant in Kingston, Ontario that day. We would have used more because we knew that 18% wasn't sufficient, and I'll come back to that. We also tried 25% slag because the highway department generally allows 25% slag in all their concrete, but you need special permission to go above that. So we wanted to see what that would do, even though we knew it wouldn't control the ASR on this one. We then used a ternary mix because in their high-performance bridge specs, a number of other high-performance projects in Ontario, they typically use a blended silica fume cement with slag, 25% slag in that as well. Now, the blended silica fume cements they normally use are 8%, but we didn't have enough bags of silica fume blended cement on site. We miscalculated, so we ended up using 3.8% silica fume in the total blend. We had a low-alkali Portland cement, about a 0.46 alkali, to look at the low-alkali control, and then we used a straight high-alkali cement, which was about a 0.8 alkali, so it wasn't super high as compared to some of the Ontario mixes. They all had a high cement content, 415, which I think is about 700 pounds per cubic yard, somewhere in that range. And they all were made with the Spratt reactive aggregate that's been mentioned previously, which is a silicious limestone near Ottawa, Ontario. And there's the description, because Chris is a petrographer, middle Ordovician, medium gray, fine crystalline limestone with about 9% silica. It's been used in a number of projects, including the work in Texas and other places around the world, because Chris set up stockpiles of this aggregate that could be used by various researchers around the world as a common sort of stock. We used commercial ready mix. There was a ready mix plant about half a mile away, so we were able to batch at the ready mix plant Some of the special cements, because it was a small plant, we had to hand bomb from a scaffolding into the back of the truck. But then we were placing the beams, reinforced on reinforced beams in the sidewalks there. And again, then we cured them for 4 days with wet burlap and plastic. This was done in September of 1991, so it was getting cool at night. In fact, it went down near freezing the first night, which was a bit early. The strengths at 28 days. There's the water cement ratios. We were targeting about 0.4 or just under 0.4 to meet the highway limits, maximum limits. But the ternary blend with silica fume had less because we used a high range water reducer because of the silica fume. So it was somewhat less, lower water cement ratio. The 28-day strengths were in the order of about 40 megapascal, which I think is 6,000 psi. And you can see that at 7 years they're up around 60 megapascals generally. The alkali loadings are there. We didn't dope any sodium hydroxide into the blocks. We used the alkalis as they were. So the alkali loadings in kilogram per cubic meter are shown there. We did accelerated mortar bar testing. We did concrete prism testing. Then we've been monitoring the blocks and the pavements. So you already know about this test, the 80-degree test. The 14-day expansions for the 6 mixes are shown there. And based on those predictions, the 50% slag mix and the ternary blend with silica fume and slag would pass the test. You can see that both the low-alkali and high-alkali cement have high expansions because the alkali level of the cement in that test has no impact because you're throwing it into a 1 normal solution, so there's no impact of the alkali. And of course, 25% slag and the 18% fly ash weren't sufficient to keep it below 0.1. And just for fun, we measured a bunch of them out to 28 days, even back then. And this gets to the heart of some of these comments or agencies that want to use a 28-day limit in this test, which I think is goofy. If you look at mix number 4 with the ternary blend, it would be 0.15 at 28 days, which would indicate it wouldn't pass. And as I'll show you, this mix has not reacted at all. We wouldn't expect it to react at all. When this test was adopted, you have to pick a test date with the test, and it's already accelerated. Using a longer test age, I think, is foolhardy. The concrete prism test, which is 1293 or the Canadian equivalent, pretty much the same thing. But in this case, we used the cement content of the mix that was 415. We didn't add alkali because we cast these beams from the same mixes out of the truck. So unlike the standard test, we didn't boost the alkalis. So this is what happened. We measured the concrete prisms over 9 years in the laboratory at 38 degrees, sealed in bags with a bit of water inside containers at 100 degrees Fahrenheit. And the 0.04 limit is the red line across the horizontal axis there. 2 years is the standard number, which is the vertical line there. It's 2 years. You can't see the numbers. And what you see is the high-alkali concrete, even without the boosted alkalis, took off very rapidly within about 3 or 4 months, exceeded that limit. The low-alkali cement was right on the border of that 0.04 at 2 years, but eventually climbed up higher, as was the 25% slag was slightly higher than the limit. The 18% ash was in the same ballpark as the low-alkali. The 50% slag and the ternary blend are the ones that are the lowest on there, the pair that are the lowest. But even if you carry it out to 6 years, they creep up there, 0.04, 0.05, but they're really not doing anything compared to as you can see, the range. So let's look at the beams. These are the unreinforced beams, and we see expansions up in the neighborhood of about 0.2, as high as 0.23. If I go back, we were measuring about 0.16, 0.17 in the concrete prism test in the laboratory at 38 degrees, but we're even getting higher expansions in the field in that same time, well, a slightly lower time frame, but in about the same time frame, we're seeing similar expansions to what the concrete prisms at 38. We're seeing this in the field in Canada, which is not the hottest environment compared to places like the Texas site. So what you see, we had a pair of identical beams. The 2 lines going up the highest there, where we had a redundant beam, and we can see that the expansions, the 2 beams expanded pretty much exactly the same. One of them was sacrificed to do some work on RCA that Medhat Shihada did after about 12 years. And you can see that the high-alkali cements expanded the most, but then the low-alkali cements expanded and cracked as well. I'm showing the 0.04, but we saw the first observations of cracking. I didn't have it put on all the graphs here, but it's in the area between 0.04 and 0.07 is when we saw the cracking in the field, that we could see visual signs of cracking. But we only went out there once a year, so we didn't maybe catch the exact spot. So we know it was less than 0.07, but maybe it was down closer to 0.04. So you see the low-alkali cement was next, and then the 25% slag, and then the 18% ash. And the only two that have not expanded over 20 years are the 50% slag and the ternary mix with silica fume and slag. So it mimics the concrete prism. And just to show you the sort of cracking, this is after 14 years. There's the 18% fly ash. We started to see minor cracking on the side of the beam. And again, with the 25% slag, you can see minor cracking. With the low-alkali cement, you see a more extensive crack pattern. So the low-alkali cement is not mitigating. And then the high-alkali cement, again, we're seeing a very similar crack pattern and some wider cracks. If you look to the left there by Chris's shoe, you'll see some wider cracks. And up at the top, and on the top, we saw some fairly large cracks as well near the measuring points. That's a plastic plug protecting the measuring point. Oops, sorry. Now the reinforced concrete beams, the expansions are lower. The restraint of the steel did restrain the expansions. So the maximum expansions, instead of being in the order of 0.23 later ages of the high-alkali cement, you can see they're about 0.12. So it cut the expansions in half, having that restraint in that direction, the longitudinal direction. But again, the same ranking is there. And of course, the numbers are lower and they're bouncing around that limit with the 18% fly ash and the 25 slag. But the visuals, we are seeing the surface cracking with those two mixes, regardless of that expansion. So the only two, again, that didn't crack and didn't expand at all were the ternary mix and the 50% slag in the reinforced bars. And that just shows 25M bars are 1-inch bars and the 20M bars are 3/4-inch bars. I can't remember the numbering system for the U.S. bars. Anyway, the pavement slabs, which are again these slabs, they're about 6 or 8 inches thick, are there. Again, the maximum expansion is in the order of 0.15, so which is intermediate between the unreinforced beams and the reinforced beams in terms of total expansion. And again, it's the same order. Here, the low-alkali cement and the slag, the 25 slag and the 18 ash didn't control the cracking. The two that have controlled the cracking over the 20 years are the ternary blend and the 50% slag. So it's consistent in all the field exposure, and it's consistent with the concrete prism data, and it's consistent with the 14-day mortar bar test. So just to compare, we took the high-alkali Portland cement because it had the highest expansion. If you compare what happens in the field versus the lab here, the 38-degree concrete prisms, the one on the left expanded faster, and the two unreinforced beams, which are the two beam 1, beam 2, reach about the same expansion at the same age, but they just took longer to get there. And the reinforced concrete beam and the slabs on grade were somewhat lower than that. But they're in the same order of magnitude of expansion, because people complain that the 38-degree concrete prism test is accelerated and you wouldn't get that in real life. And even though we don't get 38-degree weather in Ontario, it eventually gets there in the concrete. The surfaces do get that hot due to solar reflectance. You can certainly get 40 and 50 degrees under the surface of concretes in the summer there. But then we get freezing weather as well. I'm sure these would go much faster over in southern climates. But it's interesting to compare the sort of the net expansion after a long period of time, just different rates. Okay. We also did some petrographic work on the cores that we took at we took them at 12 years, but we measured them at 14. Took us a while to get our act in here. Paddy Grattan-Ballou up in Ottawa did the damage rating index where he does a petrograph. You take a polished section and you look at crack interfaces. You look at cracks in the aggregate, cracks in the paste. You look at if there's gel present, those sorts of things. There's indicators as shown by the colored chart on the right, and you add those up and you end up with a number. And the two, again, that have the lowest number is the ternary mix. There's almost no evidence of any damage. Typically, if your damage rating is around 50 or less, you typically assume it's not damage. But again, this is at 14 years. At 20 years, we haven't taken cores. It's one of the next objectives to get another set of cores to see if these numbers have risen. Of course, the high-alkali cement one that had cracked soonest had the big number up around 200 by that technique. Chris did some optical petrography on this, and we found evidence of fracturing in the aggregate. This is a quartz grain in the limestone, and you show a fracture through it. You can see the gel in here, and he identified this as oakenite, which has this formula. It's a calcium silicate hydrate, which has been found in some other work described by Fournier and Berube in the Quebec side of similar findings in some of the gel that is crystallized to some extent. And again, here's some gel in the paste of these cores. And again, there's inside the limestone here showing the gel in the paste, or extending to the paste on the left, yes. So we did Terry did some microscopy on the backscattered imaging, and this is the high-alkali cement. We can see some of the aggregate particles. The aggregate's split here and it's filled with gel, exuding through the paste. Here's another aggregate particle that's been split and exuding into the paste, and some cracks in the paste here. And we did some EDX analysis on some spots. This little image here is a blow-up from there. So it shows inside the coarse aggregate here, you're seeing fracture filled with gel. And if we take the analysis up inside, which is there, which would be there in that picture, we get number 4, which is silica and potassium and calcium. Potassium and calcium, are about the same. And then we get to number 1, which is closer to the surface of the paste. Again, we're seeing mainly potassium, about the same as calcium, so there's no change between there and there. But then as soon as it gets out into the paste, we're starting to see more calcium relative to potassium in the gel that's in by EDX. And as you get further out into a void here that's been filled with gel, we see much higher calcium and less potassium. So we're seeing this change in composition of the gel as it exudes into the paste, as some of the alkalis being recycled and calcium from the paste replacing the alkali in that gel, which has been associated with swelling pressure and by changing viscosity of the gels. This is a picture from the 18% fly ash. Again, there's some minor cracking in the aggregate. Again, there's some blow-up areas shown here. That void, we're seeing some gel in the spots there. Again, in the void here, it's a high calcium, relatively low alkali at that point. The 25% slag, again, we're seeing another fracture here in that aggregate with some gel deposits. You can see the potassium and calcium about the same height. In the ternary blend, we're seeing a little bit of gel, but we're not seeing any damage as a result. There's no cracking of the paste. This crack here, we assume, was because it's not connected to anything in the aggregate, that it's a preparation, formed during sample preparation. And of course, it's being a crushed aggregate, there are some fractures in this coarse aggregate. I will just summarize what we found. We got cracking within 5 years in the field with this high-alkali Portland cement concrete when it was outdoors. Low-alkali cement started to crack at about 7 years, even though it had a much lower alkali loading with this aggregate, so it wasn't sufficient to protect it. When we saw cracking was in the order of 0.04 to 0.07, which is just in the range of just above what we use for the concrete Prism test for limits. When we used enough supplementary cementing materials or low-alkali cement, we reduced the expansion relative to the high-alkali cement, as you might expect. And when we used sufficient SEMs, there was no sign after 20 years of ASR cracking or expansion. The damage rating index sort of tied into the relative amounts of damage we saw, although we'd like to do some more of it to see if it's progressing. The data confirms the advice in the Canadian standard that when the mortar bars give by what would be 1567 at ASTM mortar bar test with less than 0.1 with using SCMs, that seems to be sufficient to, with this particular aggregate, certainly to mitigate it. So it confirms that advice that we put in a long time ago, and now we have this longer-term data. I didn't show this data, but those SEM mixes, as you might have suspected, much lower chloride diffusion coefficients, much lower Coulomb ratings than the Portland cement mixes. So the highway department, of course, wanted to use some of these mixes for bridge decks and highway structures where chloride ingress from de-icing salt is a concern to them. So that was what they're interested in as well. So, thank you for that.
I was surprised at how little impact the reinforcement had on the expansion. You only showed about a 50% reduction, but you had 1.5%, was it?
It was, I can't remember. It was 0.23 versus about 0.15.
Right.
0.11, 0.12.
Were the bars bent at all, or were there plates welded to the end to develop the...
It was a cage. We made a cage with minimal vertical steel to hold the horizontal bars top and bottom. We had equal steel top and bottom.
Right.
And I think we had 3 hoops to hold the steel in place. But they were just tied with tie wires. We didn't have any hooks.
Okay. All right, thanks.
How were the exposure blocks and the slab fuel?
4 days a wet burlap. That we left the forms on, with the beams, we left the forms on and kept them covered. With the sidewalks, we used wet burlap and plastic for 4 days. We also had thermocouples embedded in various things to measure the thermal history. We monitored the freeze-thaw cycles at various steps over the first 10 years as well, but I didn't have time to show that data. Because that's how many bags of fly ash we had at the site. We thought we had more, but because we were doing this on the fly, we had to drive like 3 to 4 hours from Toronto, and we rented a 5-ton truck, and we thought that the local supplier had some ash, and they didn't have enough, and so we were kind of restricted by we couldn't go get any more. So we ended up using 18, even though it was an F ash, but we just couldn't get enough of it. That's all. And 18% wasn't sufficient. If you look in the guide, the Canadian standard for this particular aggregate, you'd have to use at least 25% F ash to control it. It'd be called a high reactor. And you'd need 50% slag to control it. So we knew 25 wasn't enough, but the MTO used 25 in a lot of their other concrete, so they wanted to know what impact that would have.
So you mentioned that the 14 days expansion is 0.1, and the material in the proportion used will prevent deleterious. So is it the proportion that is in mortar?
Yeah, well, we did the mortar bars with the same proportions, like the 50% slag and the 3.8 silica fume and 25 slag. That kept the expansions less than 0.10 in the mortar bars, and it also prevented the expansion in the concrete, either in prisms or in the field.
If you maintain the same proportion?
Yes. So maybe that's not clearly worded.
Okay, thank you. Thank you, Don.
Thank you.